charge. We know atoms have equal numbers of protons and electrons. So the positive protons cancel out the negative electrons, and that's when the atom isn't bonding with anything. As soon as you bond with something, you're sharing electrons. Sometimes you're donating electrons, sometimes electrons are being accepted. Either way, the electrons are moving so that they might be closer to one atom or another. So the formal charge is a way of figuring out the charge experienced by each atom in a molecule after it's bonded, especially if you have a coordinate covalent bond. Coordinate is when one atom donates both of the electrons that are being shared between the two atoms. So you're trying to see, is this atom by its regular amount of electrons, or is it by extra electrons being negative, or is it by fewer electrons than it normally is, making it positive? So if you're trying to figure out what the formal charge is, first you look at how many electrons an atom should be by. And the should, or is typically by, is how many valence electrons that atom has. So the valence electrons that that atom has, and then you're going to subtract the electrons that are actually by the atom. And the way you figure out the electrons that are by the atom are going to be lone electrons count as whole electrons being by the atom, and bonded electrons are being shared. So you can think that they're with one atom half of the time and they're with the other atom half the time. So bonded electrons count as 1/2. So if I were trying to assign formal charges to this thing, I would say for the nitrogen, nitrogen has 5 valence electrons, so it's usually by 5. And in this drawing, it has 2 electrons that are alone, so it's 2. And then it has 1, 2, 3, 4, 5, 6 that are being shared. It experiences those 6 electrons about half of the time. So half of that 6 is 3. So I'm going to have the feeling of 3 electrons from the shared 6, and the feeling of 2 electrons from the 2 alone. So that's 5. It's actually by 5 electrons, giving me a formal charge of 0. So that nitrogen's formal charge is 0. When I look at the hydrogens are all going to be the same. So I'll just do them once. Hydrogen is typically by 2 electrons. By 1, because hydrogen has 1 valence electrons. And right now it's by 2 electrons that are being shared. Since it's got about half-time custody, you could say. The electrons are spending half their time with the nitrogen, half their time with the hydrogen. We ignore electronegativity, and we say that the hydrogen experiences 1/2 of that negative charge. So half of 2, it experiences 1. So, well, that was exciting. Both of those are 0. Now we'll actually get a formal charge over here. The hydrogen you can see is the same as this hydrogen. So each of these hydrogens has a 0 formal charge. Let's just look at the nitrogen. So nitrogen, again, is typically by 5 electrons. So 5 is the normal. Let's subtract, and we're subtracting because we're looking at the negative things that it's actually by. This nitrogen is by 2, 4, 6, 8 shared electrons. And since it gets the experience of shared electrons about half the time, half of 8 is 4. So it's typically around 5. It's currently around 4. So that means it has a positive 1. So the nitrogen has a positive 1 formal charge. And this is the ammonium ion. Ammonium is when ammonia has gained an H+. So H doesn't bring any electrons with it. So we knew that this was a positive 1 charge. Now you know that positive 1 is on the nitrogen. Okay, let's look at assigning some more. So again, you're just figuring out the charge per atom. You look at how many valence electrons something is typically surrounded by, and that's going to be the base level, and you're going to subtract how many electrons it's actually by, because that's negative. It's experiencing a negative charge from a whole negative charge from lone electrons, half of a negative charge from any shared electron. So, one way you can look at formal charges, because I didn't tell you what it's used for. Typically, you try to get formal charges down to 0. You've probably, now that we're violating the octet rule, you know that it's not so much as a rule, maybe it's a guideline trying to use up S and P orbitals because they're lower energy. But maybe you're wondering, well, how do I know if I should break this rule or not? And one thing to look at is how can you minimize the formal charges. So that's one way of approaching Lewis dot structures, is getting the lowest formal charges. So here's HN3, and there's 1, 2, 3 different Lewis dot structures. So this loose dot structure is neater over here, so we can see the lines. This one just tells us who gave what electrons, and you can see there's a coordinate covalent bond because this green nitrogen is responsible for both of those green electrons. Here's the second structure, that's that guy, and then here's the third. So here's another coordinate covalent bond. This black nitrogen is donating both of those. Let's assign formal charges. First of all, the hydrogen is going to be 0 in each, because the hydrogen is typically by 1 valence electron. It's currently by 2 being shared. So let's get that out of the way. Zeros all around. It might be easier if I do it on the structure that has lines. So let's actually assign them there. Okay, moving on. Let's look at this hydrogen. Nitrogen. Nitrogen is typically by 5. This nitrogen is experiencing half of the 2, 4, 6 electrons being shared. Half of 6 is 3, so it's experiencing 3 from here. And then there's a lone pair, so 2 more, so it's experiencing 3, 4, 5. So typically nitrogen has 5 valence electrons. This nitrogen has experienced 5 electrons, so it has a formal charge of 0. Then next, we've got this nitrogen. Typically it's around 5. It's currently by 8 shared electrons, so it's experiencing half of that 8. It's experiencing 4. So 5 minus 4, it has a positive 1 formal charge. And then this one, typically by 5, currently it's experiencing half of this 4 being shared, so that's 2, 3, 4, 5, 6 for the lone pairs. So typically experiences 5, it's currently by 6, so 5 minus 6, this has a negative 1 formal charge. And then let's look at the structure. So here's nitrogen. Typically, it's experiencing 5 valence electrons. This guy has 2, 4, 6, 8 electrons being shared. So it's experiencing half of that, 4. So 5 minus 4, this has a plus 1 formal charge. This guy is going to be the same thing because it has 2, 4, 6, 8 electrons shared. 5 minus 4, because half of the 8, plus 1. And then this nitrogen has typically 5. It's being surrounded by half of this bonded pair. So half of 2 is 1, 2, 3, 4, 5, 6, 7, looking at these lone electrons. So 5 minus 7, this has a negative 2 formal charge. All right. Then over here, I have nitrogen usually has the 5 minus half of each of these bonded pairs. So that's going to be 1, 2, 3, 4. We'll experience 2 of the 4. 2, 3, 4, 5, 6. So 5 minus 6, this nitrogen has a negative 6, negative 1. Sorry. 5 minus 6 is negative 1. Alright. Lost a lone pair there. And this nitrogen would be around 5. It's experiencing half of the 2, 4, 6, 8. So it's experiencing 4. 5 minus 4 is going to be positive 1. And this nitrogen, typically around 5, it's experiencing half of the 2, 4, 6. Half of 6 is 3. And then these two, so 3, 4, 5. 5 minus 5 is 0. So what we would do with these is I have 3 different structures with formal charges. And personally, I would look at this and I would think, well, I want to have as few formal charges as possible. So these 2 structures are more likely based off of the formal charges. And the truth is, all 3 of them are going to exist. There's going to be some resonant structures, but I would believe that these are going to be maybe more common because the formal charges are less. Then we have xenon dioxide. So there's 2 ways we can draw this one. Here's xenon with its 8 electrons, 2, 4, 6, 8, and oxygen with its 6 electrons. Same thing, xenon with its 8 electrons, 2, 4, 6, 8, and oxygen with its 6 electrons. You can see in this one, the oxygens are singly bonded, and over here, the oxygens are doubly bonded. So you can see over here, you're not violating the octet rule, even though we know weird stuff is happening because xenon is a noble gas making bonds. Over here, we are violating the octet rule. So this is one of those problems where you would say, I know xenon has access to the d orbitals. Is it actually going to be forming bonds in the d orbitals or not? So one way to figure that out is, well, which one has lower formal charges? So oxygen has 6 valence electrons, so it's typically by 6. It is currently by half of these 2, so there's 1, 2, 3, 4, 5, 6, 7. It's currently by 7 electrons. So it has a -1 formal charge, and this side is like this side, -1. Since this is neutral, I can go ahead and guess this will be +2, but let's make sure. Xenon is typically by 8 electrons. It's going to experience half of these 4 shared electrons. Half of 4 is 2. So 2, 3, 4, 5, 6. So it's typically by 8. It's currently experiencing the negative charge of 6. 8 minus 6 gives me a +2. So there's the formal charges for this guy. Then over here, I can see I have oxygen's typically by 6. Right now it's experiencing half of these 4 electrons being shared. Half of 4 is 2. So I've got 2, 3, 4, 5, 6. So it's usually by 6. It's currently by 6. 6 minus 6 is 0. And then here is xenon. I know this guy will be the same. Xenon, typically by 8. Right now it's experiencing the charge of half of those 8 being shared. So that's 4. 4 from the shared. 5, 6, 7, 8. All right, 0 formal charge all around. Based on formal charge, this structure is predicted. So if you get a question on the AP chemistry test that says calculate the formal charges, that's how you do it. Full negative charge for lone electrons, half of the negative charge for shared electrons. And if it says predict the structure based on formal charges, predict the structure that has the lowest formal charge.